Welcome to Math 2320. This is our last section in Chapter 6 on power series. And in Section 6.3, we want to further classify singular points. So let's see what all that means. So we have our differential equation here. We try to put it in standard form. So we divide through by x cubed. And when we do that, we find p of x and q of x. Certainly we have a singular point at x equals 0 because both p and q are undefined there. But the question is, well, what kind of singular point? Is it a regular one or is it irregular, as that matters? So the definition comes from looking at forming small p of x and q of x, where we multiply both p and q by powers of the place where the singular point was at. So what I'm saying is we're multiplying by x minus x0, where that is the singular point x0. So for the small p of x, it's to the power of 1. Q of x is to the power of 2. And so when I do that, I'm still left with 7 over x and 2 over x. So multiplying by powers does not change the fact that it's still undefined at x equals 0. So x equals 0, our singular point, is not regular in the sense that it's still undefined there. So it is irregular singular point at x equals 0. Now in question 2, we have a different differential equation. And again, I try to put it in standard form to see what's going on. So I'm going to divide by x squared minus 4, that quantity squared. All right, so when we clean all that up, let's see what we've got. Well, first off, x squared minus 4 factors into x plus 2, x minus 2, and it's squared. So I've got x plus 2 quantity squared, x minus 2 quantity squared, all the way through. So let's see what happens. Well, in the first case, the x plus 2, one of them cancels. In the second term, my q of x, nothing cancels. So looking at where p and q are undefined, I get singular points at x equals minus 2 and x equals plus 2. So we've got the singular points. Are they now regular or irregular? All right, well, let's see. If I try to plug in and I probe with my small p and q, I'm going to use x equals minus 2. So I'm multiplying by x minus a minus 2, or really x plus 2, to the first power, and x plus 2 to the second power. So when I do that, well, what happens? The x plus 2 term cancels, and I'm left with 1 over x minus 2 quantity squared. For small q, I'm multiplying by that term squared. That cancels off the x plus 2 quantity squared, and I'm left with 4 over x minus 2 squared. So when you look at those resulting answers, if I plugged in x equals minus 2, is this still undefined? And the answer is no. It is defined at the singular point. Therefore, we say that this is a regular singular point. Well, what about if I try to plug in x equals positive 2? All right, so that means I'm multiplying by x minus 2. I multiply that by my x plus 2 squared. So the x minus 2 part cancels. One of them cancels. Sorry, that's not there. And so I'm left with this term for small p of x. Is this still defined when x is equal to 2? And the answer is no. Therefore, it is an irregular point. All right. So here we're given our point here, our differential equation. I put it in standard form, and I'm doing that by dividing by x squared. All right, so when I do that, I get my p of x term, which is this, capital P of x, and my capital Q of x, simply distributing the term in. All right, so here's P, here's Q. Certainly we do have a singular point at x equals 0, so x equals 0 is singular. All right, so I multiply by powers of that, so x and x squared. And so here's small p of x, here's small q of x. So the assumption is, because these look like this, then p and q can be written as a series representation. So matching this up, A0 is 11/6, B0 is minus 1/6. That is filled into the equation that was given to us and we saw in the section 6.3, where we fill in A0 and B0. So simplifying that, we get something that is factorable, and r is 1/6 and minus 1. So these do not differ. So if you go back up to the second part of the question, without solving, discuss the number of series solution we expect to find by the method of Frobenius. All right, so since they do not differ by an integer, there will be two series solutions using the method outlined in section 6.3 by Frobenius. All right, in question 4. So we're given a differential equation. All right, so we would take this, we would divide to put it into standard form, find our values of r, and then get the two series solutions. So they outline this pretty well for us in the solution. All right, so we are looking for a solution of this format, plugging things in and solving for what r is. We find that r is, here we go here, factor out the common r, so r is 0 and 5/4. They do not differ by an integer, so there will be two series solutions. So what do they look like? Well, using this relationship here for our coefficients, we get a relationship for r equals 0, and we get one for when r is 5/4. So putting that into the problem, separating out C1 and C2, so here's C1, we had the power of r is 0, so x to the 0 is 1. And here we had r is 5/4, so we get an x to the 5/4, C2, and the two series solutions.